Okay, in this video I'm going to go over the 5 different types of entropy that I've identified. They're radically different, and the big lesson here is that very smart people can make very dumb mistakes. Okay, to set the stage, there's a certain magic trick that I heard about from Daniel Dennett, and it's called the Toon Deck trick. Now, the whole secret of the trick is in the name, the Toon Deck trick, specifically in the word the, because it's not really a single trick, it's 5 different tricks, and the magician can change the trick that they're playing. And the reason that people don't notice it's 5 different tricks is because all the tricks look basically the same. They're just done differently. And the trick is you tell somebody, you figure out which card they picked, basically. And the reason it was so hard to figure out, magicians couldn't figure out how this trick was done for the longest time, because they were thinking it was a single trick. And so when you test your hypothesis to figure out, are they doing trick A, trick B, trick C, etc., you'll always be wrong, because the magician can keep changing the trick. So, similarly, with the concept of entropy, lots of confusion comes from mixing and matching and switching between concepts and confusing one with another. So let's start with the first original concept of entropy. This is just the idea that temperatures even out over time. A hot body will cool or lose heat energy to a cool body, but never the reverse. And this was from the early 1800s. Carnot, Clausius, and Lord Kelvin are the big names behind this idea. This one's pretty straightforward. I don't want to spend much time on it. The second idea of entropy comes from Boltzmann, and this is where most of the big changes happen in the concept. So now we introduce an idea of the importance of order versus disorder, the importance of information, of randomness, and of probability. So Boltzmann's idea was that you measure entropy by measuring the number of microstates per macrostate. And what a microstate is the exact configuration of a bunch of particles. And the macrostate is sort of what it looks like from the outside. So how many different ways could I rearrange these particles to make something that looks has the same macro properties? And the more different ways you can rearrange the particles, the more entropy there is. That was the idea. And systems tend toward, if a system tends towards disorder, to being mixed up in all sorts of different ways, it would increase in this kind of entropy. Now, Boltzmann's idea of how to use statistics to explain temperatures and the relationships between temperature and pressure and volume was very useful and very important, but his contributions to the concept of entropy have only created confusion. Now, there's a third kind of entropy, which is sometimes called Shannon entropy or information entropy. This was created actually very recently in the 1960s by Claude Shannon. And the idea is, if you want to send a message efficiently, you want to compress it into as little information as possible, which would be very dense information, and then it would be unpacked later. So in order to do this, we use information compression, which is you basically extract all of the patterns, all the redundancies from the information, and what you end up with is something that's very random. Now, someone named von Neumann discovered that this kind of resembles Boltzmann's formula for entropy. And he suggested to Claude Shannon, why don't you call this new concept that you've invented information entropy? And he did. It was never his intention to consider it to be an actual form of entropy or to suggest that there's any deep pattern or deep connection between thermodynamics and information compression. But now we're stuck with it, and unfortunately this has created even more confusion for many other reasons. The next step in the evolution of the concept was someone named Jakob Bekenstein, who actually took the information entropy and just started to believe that thermodynamics applies to information entropy. So information entropy is real entropy, and black holes, he thought, had a lot of information entropy. He thought they actually compressed information, which is kind of strange because there's nobody trying to encode a message. There's no communication going on. There's no deliberate attempt to extract all of the patterns from a signal, and there's no representations at all in a black hole. It's just, matter being condensed. So anyway, he did that. He noticed some other superficial mathematical patterns and thought this must indicate some deeper relationship. Then there's von Neumann, and von Neumann entropy has to do with quantum information. So it's basically Shannon information, but it's been applied to, instead of having sort of randomness in information, it's randomness in a quantum state, or quantum randomness. And it's basically the same idea applied there. But there are a lot of big differences between Shannon information and quantum information. One of them is that you can't copy quantum information, you can't delete quantum information, you can't modify it, or you can't hide it, you can't encrypt it. There's all kinds of things you can't do with it that you can do with regular information, because quantum information just isn't information. I think it's wrong to call it information. It just creates too much confusion. Anyway, so those are the 5 types of information. So we have the original, the Boltzmann type of, entropy, not information. Boltzmann type, Shannon entropy, von Neumann entropy, and Bekenstein entropy. I'm going to go into how these are getting confused and conflated later. I just wanted to make sure that those 5 concepts are clearly distinguished